This video was sponsored by Brilliant. Linux is not an operating system, it is a kernel. I wonder how many times I've read that phrase on the internet, and yet how few times the people who constantly repeat it care to elaborate. In this video, we're going to follow the process tree all the way back to the very first process and figure out exactly where that line is drawn. Hi friends, my name is George, and this is CoreDumped. The answer to our question comes from user processes, which might actually be surprising to many of you. The very first thing we need to understand is how processes are created. I made a video about this, but here's the summary. On Windows, a process can use a system call to ask the operating system to create a new process, and Windows does exactly that. On Linux and Unix-like systems, a process must first ask the operating system to clone itself. Then, the cloned process asks the operating system to replace its program. So there's a mostly philosophical difference in the way both systems manage process creation. But the fundamental idea is the same. User processes are created by other user processes. To make this video easier to understand, we'll explain things in Unix/Linux terms. Think about this. If all user processes are created by other user processes, that means every process has a parent process that created it. But since those parents are also user processes, they must have been created by other user processes, and those by other user processes, and so on. That means that if we trace things back, we will eventually find a single process that is the ancestor of all the user processes in the system. On Linux systems, you can actually visualize this tree by running this command. And as you can see right here, there is indeed one process at the root of the tree that is the ancestor of all the other processes. But this root process raises a question. Who created it? It couldn't have been created by another process, because then it wouldn't be the root of the tree. Believe it or not, this is where our answer can be found. Because in some way, everything that happens before this process is considered part of the kernel. That being said, let's define what a kernel is. In a computer system, we have hardware devices on one end. At the very opposite end, we have the user, whose goal is to run multiple applications. Dealing with hardware is actually very tedious and even risky, so to prevent applications from breaking things because of bugs or poorly written code, there is a very complex layer between user applications and the hardware. The very first part of that layer, the one that sits directly on top of the hardware, is what we call the kernel. The idea behind this design is that every time a user application needs the hardware in some way, the kernel manipulates the hardware on their behalf. User processes might still try to do things by their own, so extra protection is needed. For that reason, CPUs are designed to operate in two execution modes, restricted mode and privileged mode. When the CPU runs in privileged mode, it can execute virtually any instruction in its instruction set, including those required to configure hardware, manage memory through page tables, control interrupts, and communicate with peripherals such as GPUs, network cards, storage devices, and other I/O hardware. When the CPU runs in restricted mode, it is limited to executing a safe subset of instructions that do not allow direct access to hardware or critical system resources. In this mode, the processor can perform computations, comparisons, loops, and general program logic, but it cannot execute privileged instructions. Since privileged mode grants full control over the processor and system resources, the software running in this mode controls what restricted mode code is allowed to do. As you may have guessed, all user applications run in restricted mode, while the kernel runs in privileged mode. For that reason, we use two corresponding terms, Kernel-space and user space. When a user application needs to access hardware, for example, to display text on the screen or send a message through the network, it has no other option but to use a system call that invokes the kernel, asking it to perform the task on its behalf. This is the way modern systems ensure that normal user applications cannot directly access hardware, guaranteeing not only correct operation, but also system security. That layer is not a single component, though. The kernel as a whole runs in privileged mode, but inside of it there's an entire stack of subsystems that manage a specific resource or provides a specific service. Without the kernel, user applications cannot exist, because they need it to do what they cannot, due to they operating in restricted mode. The system call interface is the closest part of the kernel to user programs. So when we turn on a computer, before starting to do anything useful from the user's perspective, the executable code of the kernel must be loaded into memory in a process called bootstrapping. Once all the critical components are loaded and ready to run, one and only one user process is created by the kernel itself. This is known as init. With a process ID 1, init is the only user process that is not created by another user process in a Unix/Linux system. Deep inside the kernel's code, there's a hard-coded routine that looks for an executable file called init in the file system under one of the following paths, shown here in priority order. If we check the source code of the Linux kernel and go to init/main.c, we can see there's a function called kernel init that initializes a lot of resources and eventually tries to run init from one of those paths during the boot process. This function calls another function called runInitProcess, which we can see internally calls execve. Notice that this is not the traditional execve system call that user processes use. Since this code is already running in kernel mode, there's no need for a system call, so this variation, called kernel execve, is used to directly run the routine that loads the new process. Also notice that if the executable file is not found in any of those paths, the kernel will panic during the boot process. Now, you might be wondering, why is any of this important for this video? Because this is as far as kernel developers care about user space software. They hard-code the routine that launches the very first user process, but they do not care what that process actually does afterward. In fact, this init program is nowhere to be found in the Linux kernel source code. It is not part of the kernel. We're getting very close to our answer. But before we move on, I want you to pause the video on this diagram and think about something. What operating system services that user applications depend on are missing here? While you think about that, I'd like to tell you about Brilliant. If you're someone who likes to understand why programs behave the way they do, not just how to write them, Brilliant is a great platform for building that kind of intuition. With courses designed by world-class teachers from MIT, Harvard, and Stanford, the platform is designed to be approachable for younger learners while still being engaging and challenging for adults. One thing I love about Brilliant is how interactive it is. Rather than just watching explanations, you're constantly making predictions, testing ideas, and adjusting your understanding in real time. And if you're curious about the technology behind today's AI systems, Brilliant also has a great course called How AI Works, which walks through the core ideas behind modern AI models. To learn for free on Brilliant for a full 30 days, go to brilliant.org/coredumped, scan the QR code on screen, or click on the link in the description. Brilliant's also given our viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. And now, back to the video. What operating system components that user applications depend on are missing here? Right off the top of my head, I can think of several. The display server, the shell, the session manager, the network manager, the package manager, the SSH server for remote access, and if the system supports a graphical interface, then the desktop environment, along with everything that comes with it, a terminal emulator, a file explorer, a settings manager, a task manager. All of these are things we normally associate with an operating system, and yet, none of them are part of the kernel. If you're not familiar with some of these components, here's a brief description with some examples. We're mainly talking about Linux, but I'll also include Windows equivalents so the topic is easier to follow if you're primarily a Windows user. I know exactly what a lot of you are thinking. Wait a minute. Are you telling me that not all of the operating system runs in kernel space? Yes, that is exactly what I'm saying. A huge portion of what we casually call the operating system is actually a collection of user space processes. I think the best example to understand this is your desktop environment. KDE, GNOME, Cosmic, those docks, taskbars, window tiling systems, the abstractions we associate with a desktop, all of that runs in user mode. The desktop environment is not part of the kernel, so it does not manipulate hardware directly. Instead, it communicates with a display server, another user space process, which in turn uses graphics-related system calls to interact with the kernel and present rendered buffers to the screen. The kernel does not know what a window is. It does not know what a button, a widget, or dark mode is. What you see on the screen exists because user space software renders pixels into buffers and then requests that the kernel instruct the GPU to display them. To the kernel, it's just memory and hardware access. So, a more precise definition in this context would be, an operating system is a collection of software in which some components, what we call the kernel, runs in privileged mode, while the rest runs in restricted mode. And that is where the line is drawn. Now here's something subtle but important. All of these user processes do not just magically appear. They must be created by another process. This is where init comes into play. During bootstrapping, once the kernel finishes initializing its critical subsystems and is ready to transition to user space, it executes the hard-coded routine we discussed earlier to locate and start init. If you wonder why, is because that single user space process is enough to spawn the entire process tree we saw before. From that moment forward, the rest of the operating system emerges, not directly from the kernel, but from user space code that builds the entire service infrastructure on which applications depend. If you run the process tree command on Ubuntu, for example, you'll see that the root process spawns things like the network manager, the job scheduler, logging-related services, and a large number of desktop environment processes, which on Ubuntu means GNOME. You'll also see Wayland, the display server. And here we can even see how the init process spawns Snap, the package manager everybody loves to hate. In summary, a lot of processes that make Ubuntu feel like Ubuntu. Here's the process tree on a Fedora machine for comparison. The most obvious difference is that there's no sign of GNOME on this system, which makes sense because I'm running a version with the KDE desktop environment. What we're looking at here, in other words, is how this root process is responsible for spawning the services and applications that define the behavior and personality of your favorite distribution. This also explains why there is no such thing as a default version of Linux. Linux developers only ship a kernel. Ironically, that kernel by itself is completely useless without user space programs running on top of it. It needs those programs to actually provide functionality. If you've ever wondered how Linux distributions are created, there's your answer. They all share the same kernel, but the service infrastructure built on top of that kernel varies according to the design philosophy of the distribution creators. In fact, even the root process shown in the process tree might have a different name. That's because there are multiple implementations of init, from more traditional ones like sysv init, openrc, or runit, to more modern and complex ones like systemd. As I mentioned earlier, the kernel doesn't really care how this process works. Because of that, different projects have developed different philosophies about how init should behave and what responsibilities it should or should not have. Traditionally, the idea was simple. Take your preferred init implementation, compile it as init, and place it in the system binaries directory or any of the other directories expected by the kernel. However, for historical and practical reasons, modern systems often compile the executable with a different name and place it somewhere else. In the expected directory, they simply place a file called init, which is actually a symbolic link, kind of like a shortcut, to the real executable. If you don't believe me, just go to the system binaries directory and list the contents with details. You'll see that the init file actually points to another file located somewhere else. So in Ubuntu, for example, the kernel believes it is launching a program called init, but in reality it is launching systemd. And that subtle indirection perfectly illustrates the point. The kernel only cares about starting the first user space process. What that process actually is, and what it goes on to do, is entirely outside the kernel's concern. Although the kernel does grant this process a couple of special properties. The first one is that it always receives ID 1. Normally there's no guarantee about what process ID a program will receive, but this one is always guaranteed to be 1, simply because it is the very first process created. That also makes it easy to identify in tools like task managers. The second one is less of a privilege and more of a responsibility. Init should never terminate. And the reason is actually quite simple. The kernel does not like orphaned processes. Imagine a program that spawns a Firefox process. The parent-child relationship here is pretty obvious. But what happens when a process terminates while its children are still running? A process cannot have a parent that no longer exists. So when a process, or a group of processes become orphaned, the Linux kernel reassigns its parent to the init process. In other words, init should always run because the kernel needs it to adopt orphaned processes. So even though the kernel doesn't really care what init does, it does require it to stay alive. You can try sending it signal 9, known as sigkill, and it won't terminate. The kernel cares so much about this process never terminating that it simply refuses to deliver the signal. Because it never terminates, many init implementations are also written as a recovery mechanism. If a critical service crashes, for example the desktop environment, init may automatically restart it. If for some reason init itself crashes due to a bug, or even if it exits without errors, the kernel will panic, even though nothing inside the kernel itself failed. So init does have a few special privileges, but always keep in mind that it does not run in kernel space. Now, I originally planned to end the video right here, but while editing, I realized there's actually another line we could try to draw. This one. The line that separates the kernel from the rest of the operating system is fairly easy to define. Every part of the operating system that runs in privileged mode is part of the kernel. But what about the rest? I mean, if all of these components of the operating system are just regular user space processes, then where exactly do we draw the line between the operating system and user applications? Operating systems usually come with pre-installed software. Virtually every modern operating system, for instance, ships with a web browser, usually Firefox in the Linux world. Does that mean the browser is part of the operating system? Most people would argue no, because a web browser is not essential to the system's operation. But we could make the same argument about graphical user interface tools like the File Explorer, the text editor, the system monitor, the task manager that comes with the desktop environment, or even the desktop environment itself. After all, there's nothing those programs do that you couldn't technically accomplish through the terminal and the shell. Does that mean these are just user applications and not part of the operating system? Personally, I don't think so. I think the desktop environment and the applications that come with it are precisely what make an operating system feel unique. Of course, opinions on this are subjective, but consider an operating system like Mac OS 9 in the 90s, which was designed around the idea that users should never have to type commands to use their computers. Those systems had no shell and no terminal emulator. Everything you wanted to do on your computer had to be done through the graphical user interface. In that environment, tools like the File Explorer, Task Manager, and Settings panels were absolutely essential because they were the only way to interact with the system, even though they were just user space processes. So what I'm saying is that this second line is much harder to draw. To me, that line is a bit blurry, because how do we even define the user space part of an operating system? Is it every program that ships with the OS? Every program that has no lower-level alternative? The closest thing I can think of to a definition might be this. Every program started automatically by init, since those are theoretically the essential services. But even that definition has problems. Some essential tools are not started by init because they aren't needed until the user explicitly invokes them. The terminal, for example, or the core utilities, the collection of programs that comes with virtually every Linux distribution and provides all those small but essential commands you use in the shell. Most of those programs are not started by init, and even though we all agree they are user processes, it's hard not to think of them as part of the operating system. I mean, imagine using the terminal without any of those commands. Linux wouldn't feel like Linux. So honestly, I don't have a definitive answer for this second line, and I'm curious to hear what you think. So I'll be reading your thoughts in the comments. I'm going to go ahead and wrap things up for now. Don't forget to subscribe if you want to learn more. If you want to support the channel, please check out the sponsors in the description below. And if you enjoyed this video or learned something new, please hit the like button. It's free and it helps me out a lot. See you in the next one.